Hello everyone and welcome back to our series of lectures on Introductory Materials Informatics. In the last few lectures, we have initially started with this composition-based feature vector, and then we have started moving towards description of structures. Specifically, we have talked about description of crystal structures, molecules, and now we are talking about the description of microstructures. Now, when we talk about the description of microstructures, by and large what we have been doing so far is we have been looking at spatial correlations between the different local states inside the microstructure, and then essentially describing the entire microstructure in the terms of a probability function. So what we are going to do for today is talk a little bit about how, when we have this probability functions available with us, we can do microstructure reconstructions, and then we will also talk a little bit about how it is useful for us to think of microstructures in the form of graphs, and that is where we are going to introduce the concept of Markov random fields. So by and large we will be discussing about microstructure reconstructions and Markov random fields today. Now, as we start, I just want to introduce this term of semantic segmentation over here. So when we talk about semantic segmentation, the goal over here is to classify every pixel in the microstructure or in any image for that matter into a particular category. So we are essentially doing a bit of a classification over here, where we are looking at every single pixel inside the microstructure, and then we do the classification process. So unlike a simple classification which will tell us only what objects are present, when we do semantic segmentation, it is also going to tell us where these objects are present. So if I take the example of any everyday picture, let us say you are going out and you take a photograph of a street, then with our semantic segmentation algorithm, one can start labeling each pixel as whether it belongs to maybe the street itself, whether it belongs to some sort of vehicle or some sort of dog which is running around, or a human being that is walking, and so on. So we will be doing this type of classification when we are talking about semantic segmentation. And this thing is actually very critical when we are looking at real world application. We are of course going to talk in terms of microstructure informatics, but even outside of the field of materials, semantic segmentation has enormous utility, whether you are talking of things like medical imaging or autonomous driving, the futuristic cars. There again semantic segmentation is important, because in case of, let's say, autonomous driving, the car's computer actually has to figure out which part it should go towards and what is the road, what are the obstacles present, and so on. And this is something we are also using quite a bit in case of microstructure informatics. Now, usually when you are doing semantic segmentation, it will be relying on some sort of a deep learning model, maybe some form of a convolutional neural network, which is again something that we are going to talk about in the second part of today's lecture. So this is something which moves us closer to enable the machines to get almost a human-like understanding of the visual scenes. So in this case, the visual scene are the scenes which correspond to the microstructure. So this is a very nice publication which came out in 2012, where they have used semantic segmentation, and what you can see is you can start with a microstructural image, where in this case you have got very nice dendritic features that are developing. Then what you basically do is you will do a binary segmentation of the image. Essentially you are doing some form of a thresholding. So as you do the thresholding, you are essentially dividing the image into two different types of bins, and each bin will store one specific type of phase. So in this case, the two types of phases would be the dendritic phase as well as the other one being the interdendritic phase. And then after that, with the help of semantic segmentation, one is able to detect the edges in the microstructure. So what you can see over here, you can actually start detecting the boundaries of the dendrites very clearly. in the microstructure. Okay, so this is basically what's happening with semantic segmentation, and one can use a variety of image processing tools in this workflow. So things like ImageJ or OpenCV in Python, MATLAB, all of those tools can be used in order to do semantic segmentation. Now, this is a concept that I just wanted to introduce at this stage because you should have an idea of where we are headed towards. We will head towards semantic segmentation. We will head towards doing convolutional neural networks towards the later part of this lecture. So I just wanted to introduce this concept in the beginning, but we will get back to where we stopped last time, which is where we were having our discussion on 2-point statistics, and then again restart from this 2-point statistics and then starts moving towards this semantic segmentation and convolutional neural network. So to recap very quickly, when we are talking about 2-point statistics, essentially we are trying to map probability distribution functions, and essentially the probability is that if I take a straight line of a certain length, let us say I'm taking a straight line of a length r, what is the probability that if this line has an angular orientation of theta and phi? So when I say theta and phi, theta is in the xy plane and then phi is again going into the plane, right? So I'm talking about a 3D microstructure. So if I have a straight line of length r oriented as theta and phi, which is placed randomly in the 3D microstructure, then what is the probability that the straight line is going to connect such that the first phase is lying on, the starting point of the line is lying on phase I, and then the ending point of the line is lying on phase J. So this is basically what my 2-point statistics is going to give us. Now again, I said theta and phi, but by and large we can just restrict ourselves to theta, because when we are working with microstructures, in most cases we are not doing a 3D reconstruction of the microstructure, and we are just doing looking at 2D microstructures. So we can just talk about r and theta instead of r theta phi. So again, going back to one of the examples we had taken up about a spinodal microstructure. So here we have got the two different phases that are forming after spinodal decomposition. So we can call them alpha 1 and alpha 2. And suppose our alpha 1 happens to be the dark phase and then alpha 2 happens to be the bright phase. One can then do a thresholding into getting this type of binary contrast for the microstructure of the spinodally decomposed alloy. Once we have the starting microstructure, then one can look into the 2-point statistics and start plotting out the autocorrelation functions for the black phase, the autocorrelation function for the black and white phase, and so on. So when I say autocorrelation function of the black phase, essentially what I'm saying is, if I am trying to look at the microstructure function at a location r, and then I'm going to take the product of when this goes to, let's say, r plus r prime. So that means I'm talking about a point lying at a location r, and then I am looking at a line which is described by r prime, and then I am looking at the correlation between the point over here and the point over there. Now here at the center of the image, if I have got a black phase, black colored phase, then the autocorrelation right at this point is going to be extremely bright, because when I'm looking at the center only, then the 2-point statistics function is going to become mr times mr plus 0. In other words, I would have m square r. Now this brightness depends on the scale over here, right? So if I am getting the value of m square r at the center of the image, then essentially this is going to correlate with the phase fraction of the material. And since this at the center point I already have the black phase, it is going to correlate with the phase fraction of the black phase. Okay. So one can start making this autocorrelation functions, and these would be one way of representing the microstructures. Now let us slowly start moving into reconstruction of the microstructures themselves. So So when we are looking at microstructure reconstruction, our goal is basically to obtain the probability distribution function of the local states, which we also call the microstructure function. So once the probability distribution is captured, it can be used in conjunction with some kind of a random seed in order to reconstruct the entire microstructure. Now, when we are talking about microstructure informatics, by and large what we are trying to do is we are trying to extract quantitative features. So quantitative features would be things like grain size, the distribution of the shape of the grains, the spatial correlations between the phases, the 2-point statistics, etc. from the microstructural images, and then use those features for doing materials design and property prediction and so on. So when you are collecting the data from microstructures, this microstructural data, whether you are using a method like an optical microscope or a TEM or a SEM, or maybe if you are looking into three-dimensional microstructures, you might be doing some form of tomography in order to capture the images. What you will notice is that these images will often have some amount of noise. So if I look at the original microstructure over here, you can start seeing some sort of blurriness at the edges which is coming about because of the noise. So if you have the imaging noise, this is going to create some form of obstruction when you start doing further microstructural informatics. And this imaging noise, essentially it can be in form of maybe some sort of random fluctuations of the pixel. It could be some issue at some pixels in the detector. So what we want to do is we would first want to go ahead and denoise the image to the extent we can. And so by denoising, we basically get rid of some of the artifacts. Maybe if you are looking at a microstructure which has not been very well polished, maybe there's a small scratch or something. So by denoising, what we are trying to do is we are getting rid of pixel errors or small artifacts in the microstructure which do not really represent the physical features very well. Okay. So here the microstructure has been taken from the paper over here, where the authors were looking at nickel-wedge superalloys. And nickel-wedge superalloys essentially have two different phases. There is a dark phase. In this case, the gamma phase is showing up as a dark phase, and then the gamma prime phase is showing up as the bright phase. So after the binary segmentation is done, in other words, after you do some sort of thresholding, we are in a position where we can actually do the edge detection over here. After the edge detection is done, now you are in a position where you have already started extracting some of the structural features. So from here, from this binary segmented image, you already have information in terms of the phase fractions, what is the fraction of boundaries between the gamma and gamma prime, what is the effective size of the gamma prime, do you have some gamma prime phases which are longer than the others, so that is in terms of the aspect ratio, the size of these phases itself. In addition to that, one can actually combine the elemental descriptors. Essentially, this is where your CBFE type of thing can be brought in. Then you have the compositional descriptors or the composition itself. One can also bring in the processing descriptors. This is going to be a little bit more advanced topic which we are going to discuss later on when we talk about processing structure property linkages. But by and large, think in terms of elemental descriptors and the compositional descriptors. So what you have done now is you have created a set of features which is immense, because you have got structural features, and imagine all of these different types of structural features are associated with every single pixel in the image. In addition to the structural features, you also have the elemental descriptors and the compositional descriptors, and because you know the composition at every single pixel of the image, if you have done the EDS mapping of this material as well, then those things get attached to every single pixel. So as a result of that, now you have a huge number of features that is beginning to describe the microstructure. And as we discussed last time, when you have a situation like that, the next step to do is some form of a principal component analysis. So once you do the principal component analysis, now you have got a much shorter list of features, and with this you can do some form of machine learning. So in this case of this paper, the authors were doing Gaussian process regression, but it really depends on your problem which type of machine learning process you want to do, and then after that you can start predicting the properties of the material. Now one can also look at microstructures as what we call a Markov random field. So this is a slightly different way in which we are now moving towards the microstructural description over and above the traditional 2-point statistics. And when we talk of a Markov chain, this is something that Wikipedia actually does a very good job of defining concisely. Wikipedia says that a Markov chain or a Markov process is a stochastic model describing a sequence of possible events in which the probability of each event depends only on the state attained in the previous event. So you can think of it that whatever is happening next is going to depend only on the state of the material at this juncture of time, and then the thermal history or basically any form of history of the material does not matter. So you can think of Markov chain as some mathematical model which can be used to describe a system which is moving from one state to another, and this process is essentially a memoryless process which is governed only by probabilities that depend on the current state and not on any of the previous state. Now, why is this really important for microstructures? How can this Markov chain processes help us in describing microstructures? Well, this is useful because when you think of materials, these materials often show a very complicated set of patterns as far as the microstructure is concerned, in terms of grains having different shapes and sizes, in terms of the different phases which are present, and even in terms of the defects which can creep into the microstructure. Now, capturing these patterns in a very compact and at the same time accurate manner is quite critical in order to do further microstructural informatics and to do some form of property design. And Markov chain is essentially going to provide us with a statistical framework to do this. So for example, you can think in terms of representing the microstructure as a sequence of states and then estimate how likely it is for that microstructure to transition from one phase to another phase at different positions. And once you are able to do that, you can then start bringing in again the concepts of 2-point statistics. You can encode the spatial correlations of the microstructure in a form which is much more tractable as far as the mathematics is concerned. And then once you have trained the Markov chain models, the idea is they will represent not only the existing microstructure using which you have trained the model, but also they have the ability to generate the synthetic microstructure with similar features. Because always remember, when we are talking about mathematical functions that describe the microstructure, we are basically talking about probability distribution functions. So once you capture this probability distribution function using this Markov chain model, one can then look at different scenarios in which the probability distribution functions plays out in a slightly different way. In that sense, you can think of the Markov chains as providing a bridge between the raw microstructures that you have captured and the usable statistical models which can be used for machine learning. So when you think of this Markov chain processes, it is useful to think of them in form of a graph. So if you look at the first image over here, essentially we are leveraging the framework of what is called a Ising model. So this is a fairly simple system, and what we have over here is just a square lattice. And in case of Ising model, what happens is, let us say you have a reference atom, I call it atom 1, then it has, or let me call it atom 0, and then it has got, in this particular case, 4 different nearest neighbors, which I am marking as 1, 2, 3, and 4. Now, in order to understand how this type of configuration can change, in case of Ising model, what we do is we compute the Hamiltonian, or basically the overall total energy, as a result of the interactions of the neighboring atoms with our reference atom. Now, in many cases, we simply terminate this interactions to the first nearest neighbor, and that helps us keep this model fairly simple. So basically, depending on what type of neighbor is there sitting next to my reference atom, I can have an interaction energy. And then what I do in case of a model like the Ising model is, I will try and see if I can flip the state of these atoms and then recalculate the energy. The energy difference then becomes something which can be used as to create a probability that this transition is actually going to happen or not. So this is basically the Ising model, and here what we are saying is this pixels, these are going to take binary states. So the states are described in terms of zeros and one, and we are looking at the nearest neighbor interaction in order to compute the energy. And based on the energy fluctuations, as we change the states, we decide how the microstructure of the material is evolving. Now, using our concept of Markov field, we can build upon the basic concept of Ising model and then start representing this Markov random fields as a graph model. So here what we are doing is, we are allowing a lot more number of states. So instead of just saying that the pixels will take binary states, we now say that the pixels can take integer states. And then what we are also doing is, we are now looking at higher order interactions. So as you can see in this Markov random field type of thing, this atoms are again the nodes of your graphs, and then there are lots of edges in terms of lot of interactions between different atoms, and not just the nearest neighbor atoms that we are looking at, that we are considering. So if you think about it, at the very core, this microstructures can be thought of collection of spatially arranged phases or grains. And from that perspective also, if you use a graph based model, those are very natural ways of capturing the spatial relations. So essentially, when you are thinking of this microstructure graph models based on this idea of Markov random field, what we are doing is, we are starting with the input microstructure, and as we start with the input microstructure, we now take a arbitrary neighborhood around a reference atom, and then based on how this neighborhood looks, essentially this neighborhood is being used like a template in order to determine what the probability distribution function would be for an unknown pixel. So once that is done, once we have a neighborhood like this identified, we will essentially do a search type of algorithm during the first iteration, and once that search is done and we know what the probability function is, we can come up with the initial synthesized image. So just to give you an idea, if you can start with an input image which looks like this, you can create larger reconstructed images with Markov random functions. So if you now look at the input image and this reconstructed image, what you will notice is these images look visually very similar. If you look at it pixel by pixel, point by point, you will see that these are actually different images. They are not identical images, but they are definitely similar images. So when we talk of similar images, what we are basically meaning is that the probability of finding different phases, if you compute from the reconstructed image as well as the original image, the probability of finding different phases is actually going to be the same, or at least fairly identical. So just to give you an idea, a little clearer picture, you can see that these images, they have got a number of different states or number of different phases. So for instance, you have got this phase which is your almost like a orange or dark yellow phase. Then you have got a red phase, then you have got a purple phase, and then you also have a blue phase. Okay, so you have got roughly 4 or 5 different types of contrast, because even if you look at the purple, you will see that there's a dark purple and then there's a light purple. So you've got 5 different types of contrast. And so if you now start plotting the intensity distribution, frequency distribution of this different type of phases, you will see that by and large the frequency distribution is looking fairly similar. It's not exactly the same, because this is after all a probability function, it's not deterministic, but by and large you can see that the relative distribution is going to stay the same, that you have the maximum frequency of this yellow phases or this orange type of phases, and then you have the minimum frequency of this sky blue type of phases. So those distribution statistics gets captured when you are using this Markov random field type of approach.